Hello, how's everybody doing today? Today we will investigate the 8th experiment in Labflow for CHEM 1406, which is acids, bases, buffers, and pH. First of all, what is an acid? There are at least 3 different definitions for acids and bases. The 3 definitions coexist because each one explains a different characteristic of acids and bases. Arrhenius, in 1880, defines a base as a substance that produces OH- ions in aqueous solution. A base is a substance that produces hydroxide ions in aqueous solution. And Arrhenius also defines an acid as a substance that produces H+ ions, protons, in aqueous solution. This is one definition. There is another definition. The Bronsted-Lowry in 1923, a little bit later, and they define an acid as a proton donor. What is a proton? It's a hydrogen cation, a hydrogen ion, an H+ ion. So an acid is a proton donor, and a base is a proton acceptor. So all these definitions will help us recognize when we have an acid and when we have a base. The easiest bases to recognize are the ones that have an hydroxide group, which is an OH- group, because the OH- group can accept a proton to form water. Just as a general info, acids are in lemons, in vinegar, in batteries, and they have a sour taste. They dissolve many metals, and the blue litmus paper is when we are in the presence of an acid, the acid will turn the blue litmus paper red. That is something that you can remember. And bases have a bitter taste, and there are in many household products like drain openers, antacids, and because of the bitterness, they are less common in food. However, the coffee and the dark chocolate, they have bitter flavors, and many people enjoy the bitterness. And if you are in the presence of a base, bases turn the red litmus paper blue. So what are today's objectives of this experiment? What do we want to learn? Number 1, we are going to measure the pH of several solutions. Number 2, we are going to calculate the pH. Number 3, we are going to observe the effect of us adding an acid or adding a base to buffers and unbuffered solutions. And the last thing we're going to learn today is to perform a titration of acetic acid in vinegar. And we are going to calculate the molarity and mass volume percent. So we have a lot to learn. And as I always do each week, first I'll give you a quick overview of the experiment. Then we will do a learning check and we'll perform some practice problems that it will be useful when you have to encounter the pre-lab quizzes. And after that, we will go over the report and do the calculations so you know what to do when time comes to complete your report. So let's start by looking at the write-up of this experiment: acids, bases, and pH. So the first thing we can see, we see two equations. And to recognize an acid, first thing we need to learn how to recognize an acid. We recognize an acid, in this case, HCl. We need to look for ionic compounds that have hydrogen as the cation. If you look at HCl, hydrochloric acid, it says here H plus donor. Then it has an H plus, means it is an acid. So we recognize an acid very easily because it has a hydrogen H plus as the cation. How do we recognize a base? Here, the easiest base to recognize are the ones that have hydroxide, OH. This is an ionic compound, sodium OH, sodium hydroxide. And how do we know it is a base? Because, first of all, it has a hydroxide group as the anion, OH minus. And the hydroxide anion that we can see here can accept the proton to become water. So these are the easiest way. If you see an acid and you see an H plus, you know it's an acid. It has an H plus as the cation. And the OH as an anion is an indication that you are in the presence of a base. In today's experiment, we see here these two equations. And this is pretty clear that how are we going to recognize the this is a strong acid and this is a strong base. How do we know that is a strong acid? That is another concept that we have to learn. Strong acids dissociate completely in water. What does that mean? Hydrochloric acid, all the H from the hydrochloric acid in presence of water will separate. You see here an arrow in only one direction. That means that we won't have HCl anymore if we combine the HCl, the hydrochloric acid, with water. it will completely separate. So all the H in water will be as hydronium ion. That is strong. And here we have a strong base because the sodium hydroxide, also we see an arrow in only one direction, which means as soon as the sodium hydroxide is placed in water, it's going to separate the cation, sodium plus, and the hydroxide ion, which means in water, we will not, once we place it in water, we won't find the compound, the entire compound together. It will divide into the hydroxide and sodium completely. That's why the arrow is pointing in just one direction. So this is when we say that a strong acid dissociate completely in water. And what happens with weak acids? Weak acids only dissociate partially, and the reaction is reversible. As you see the water, H2O, dissociate in hydronium ion, which is equivalent as an H plus, because it doesn't exist as itself, H plus, but you can think of it as an H plus water, H2O. It's basically sticking to a molecule of water, but you can think of water also as one dissociating into one OH and one H plus, if that makes it easier to remember. But we see that water dissociate in proton and hydroxide, but we don't see an arrow here pointing in only one direction. We see two arrows. What does that mean? That is a weak acid. Actually, it's a weak acid and a weak base, because weak means not the whole water is going to divide in two. In water, you will find H2O without separating. Part will be H3O plus and part will be OH minus. You will find the three species because it dissociates partially and the reaction is reversible. So we have different kind of acids, and each acid has a different strength. How do we measure the strength? The strength is how much the acid dissociates. Strong acid, we said, as hydrochloric acid, dissociate completely, and some acids dissociate more than others. How do we measure the strength of a weak acid? We measure that with the acid ionization constant. For example, here they are telling us the Kw. For water, we have this equation. 2 molecules of water dissociate in hydronium ion plus hydroxide. And the equilibrium constant for this reaction is just the product of the concentration of the two ions. Here, Kw equals the concentration of the hydronium ion times the concentration of the hydroxide ion. And because experimentally this constant is 1.0 times 10 Here it says 14. That's an error. I cannot write here because I'm sharing an application. That makes the situation different. But this should be 1.0 times 10 to the minus 14. We will go over later when we do practice problems. This is just the first reading of the write-up. And because the water has, when it dissociates in the same amount of hydronium and hydroxide, we say when the concentration of hydronium ions equals the concentration of hydroxide ions, we say that the solution is neutral. We will go over that. So with this equation 1, if we have the constant, it's always going to be at 25 Celsius, is always going to be the kW of the water 1.0 times 10 to the minus 14. That means that if you know the concentration of hydronium, you can calculate the concentration of hydroxide. As I said, we will go over in the practice problems. And then it comes, it's talking about that the water is amphoteric. What does that mean? The water can act as an acid because it can donate protons, or it can also act as a base, accepting protons. That makes the water amphoteric. And we already said that in pure water, the concentration of hydronium and hydroxide are equal. And we said the solution is neutral. So every time you hear that the concentration is neutral, what does that mean? Neutral means the concentration of hydroxide, OH minus, equals the concentration of hydronium, H plus, or H3O plus, and is going to be 10 to the minus 7. So the pH is defined as you see here, minus log of concentration of hydronium. So if the concentration of hydronium is, if we have a neutral solution, the concentration of hydronium is going to be 10 raised to the minus 7, and the pH then will be 7. So 7 means it's a neutral solution. Now, when we have, let's see here, the concentration of hydronium is higher than the concentration of hydroxide, we are in the presence of an acidic solution. And because the pH is defined as minus log of concentration of hydronium, if I have a concentration of hydronium that is 10 raised to the minus 2, the pH was going to be 2, and it's going to be acidic. So with this definition, we see that if we have a pH 7, the solution is neutral. Same amount of hydronium than OH minus. If the pH is lower than 7, the solution is acidic. If the pH is higher than 7, the solution is basic. Then, if we continue looking at this write-up, they are giving here an example of, it says, suppose the concentration of hydronium ion in solution is 1.04 times 10 to the minus 3 molar. So they are giving us the concentration of the OH minus. And, no, sorry, the hydronium, the H3O plus. And they are asking us to calculate the concentration of hydroxide and determine the pH of the solution. So for that kind of problems, you know that the Kw is always, as is shown here, 1.0 times 10 raised to the minus 14. So the concentration of hydronium multiplied by the concentration of hydroxide is always going to be 10 raised to the minus 14, which means it's a constant. If the concentration of hydroxide is higher, the other is going to be smaller. In this case, the concentration of hydronium is 1.04 times 10 to the minus 3. So when we solve this problem, just using the Kw, we get a concentration of hydroxide that is 9.62 times 10 to the minus 12. As you see, the concentration, which concentration is higher? The hydronium ions or the hydroxide ions? One is raised to the minus 3. Which number is bigger? Obviously, 1.04 times 10 to the minus 3 is a bigger number than 9.62 times 10 to the minus 12. What does that mean? Means that the concentration of hydronium ion is higher. What does that mean? That is going to be an acidic solution. We said that if the concentration of hydronium ions is higher than the concentration of hydroxide ions, the solution is acidic. And now to calculate the pH, they are showing us they're just using the definition minus log of the hydronium, the concentration of hydronium, and they get a number that is 2.98. Again, it's showing us that the solution is acidic because the pH is below 7. And the hydroxide ion concentration is much smaller than the hydronium ion in the solution. Let me go back to the, so I can see if there are questions here. Do you have any questions? Then we will continue with buffers. What are buffers? That strange word. Well, buffers are solutions that resist a change in pH. Again, there are solutions that resist a change in pH by neutralizing the acid or the base that we add. So basically, if we are in the presence of a buffer and we add an acid or we add a base, the pH won't change that much. And buffers are very important in everyday life. An important buffer in the blood is a mixture of carbonic acid, H2CO3, and bicarbonate, HCO3 minus. Many solutions need to maintain an almost constant pH, and the blood needs to be between 730 and 745, 7.3, because many proteins only function within that narrow pH range. So it's so important to maintain this pH nearly constant, and that's why our body uses buffers to resist those pH changes. What is a pH change? For example, let's say that we add, just to say a number, 0.01 mole of sodium hydroxide, sodium OH, to a buffer that is 0.1 molar acetic acid and 0.1 molar acetate. The pH will change from 4.74 to 4.83. I measure the pH before I add the base and after I add the base. Only changed 0.09 points. But when I add the same amount, 0.01 mole of sodium hydroxide to water, let's say I don't have a buffer, the pH changes from 7, before I added the pH of the water, to 12, pH 12, 5 points. That's why it's so important it's so important in many systems to have buffers to maintain the pH nearly constant. How do they work? Here is showing how do the buffers work. Here we have an example of this is carbonic acid. So let's say I have a buffer of usually a buffer is a weak acid and its conjugate base, or a weak base and its conjugate acid, which means this is a weak acid, carbonic acid. Which one is the conjugate base of the carbonic acid? Is this one, HCO3 minus. So a buffer usually is, as I said before, when is usually is a weak acid and its conjugate base. So how do they act? What do they do? If I add a base, which is an OH, the base is going to react with the weak acid to produce the conjugate base of the weak acid. And if I add an acid, let's say here is written, the arrow is pointing to the left. So when I add a base, it reacts with the acid. But if I add an acid, H3O+, it will react with the conjugate base of the weak acid to form more acids. So this is how the buffers act, how the buffers maintain the pH nearly constant. We can make a buffer just dissolving acetic acid and sodium acetate. So buffers are usually weak acid and its salt. What is important is that this pair of compounds are different only by a proton. So look at here, H2CO3. And look at the conjugate base. It's only missing one product. The H2CO3 lost one proton, and that is the only difference. So a buffer is just the acid and the conjugate base, and the difference is just by one proton. And in this experiment, we will study how buffer solutions and unbuffered solutions are affected when we add acid or when we add a base. Let's continue with the right. So this is one part of buffers of today's experiments. Then it says the next part, acid-base titration. What is a neutralization reaction? Here it says neutralization reaction. What is a neutralization reaction? That's easy. Neutralization reaction is when an acid reacts with a base. Here they are giving an example. An acid has an H, it's an acid, hydrochloric acid, reacts with sodium hydroxide to form a salt and water. Every time you have a neutralization reaction, an acid reacts with a base to form the salt and the water. And when the neutralization reaction is complete, the concentration of hydroxide ions equals the concentration of proton ions. And now we are going to learn what is a titration. Everybody says acid-base titration. Okay, what is a titration? We are going to perform a titration in this experiment. And a titration is just a method to determine the concentration of an unknown. In our case, we have vinegar. And we know that inside the vinegar, we have a percentage of acetic acid. We know, but we don't know how much. So we are going to perform a titration to know the concentration of the acetic acid, how much acetic acid is in the solution of vinegar. So it's just a method. We will look at the setup, and let me see if they are showing here some point. Okay, this is the setup of the titration. We slowly add a known solution. So this is the start. Let's look at A. In C, what we have is the whole setup of the titration. If you happen to be in the lab, this is what you have to assemble. You need a flask here. You need, this is called a burette, and this is what you fill. You use a beaker to fill the burette, and you use a clamp, and this is the whole setup. So in A is how you start. This is how you are going to perform a titration. In the flask here, you are going to add a known amount of your analyte. Analyte is your unknown. We call it analyte, which is what you are trying to analyze. In our case, is the vinegar. But in the titration, we need to measure with a volumetric pipette or volumetric glassware. We need to know exactly the volume of the vinegar that we use for our calculation. So we have to be precise and know exactly the volume. That's something we are going to use in our calculations. How much vinegar I added to that flask in A. So this is how I start. I place my analyte, in this case is our vinegar, and a few drops of indicator. The indicator in this case is phenolphthalein. What is the purpose of the indicator? The indicator is when up the titrant. You see, it looks like there is a, can you hear, can everybody hear me? Okay, so let's continue then. So this is how, we were saying that this is the setup of the titration, and this is how we start. We place our analyte and the indicator, in this case is phenolphthalein, and it will tell us when to stop adding the titrant. What is the titrant in this case? The titrant is the solution that we are adding, in this case, sodium hydroxide. So we will add drop by drop until the pH changed, until we see a change in color. We will go over that, and at the equivalence point, which is when the number of moles of the base is basically a neutralization. So the number of moles of the base is stoichiometrically equal to the number of moles of acid. At that point, the titration is complete. At the end point, the indicator will turn pink, light pink. And then we stop and we record the volume in the burette of sodium hydroxide. So as we said, we will determine the concentration of acetic acid in vinegar. And we will titrate the vinegar with sodium hydroxide. And once we reach the end point of the titration, the phenolphthalein turns pink, and all the acid is neutralized. That means as soon as all the acid is neutralized, we see the end point, we see the change in color, and we record the volume of sodium hydroxide. And obviously we trust on the end point, where the indicator changes the color. So with the correct indicator, the end point of the titration, which is when the color changes, is very close to the equivalence points, where the amount of acid equals the amount of base. Because the acid form of the phenolphthalein, as you see in A, is colorless, and the conjugate base form is pink, as you see in B. So one drop of the base close to the end point is usually enough to change the color of the indicator. So this is the titration that we are going to do. And then let's go almost buffers. What else is in here? The titration, we talk about that. Here is showing that when we are going to read the burette, it's always important to be at eye level and to read the lowest part of the meniscus. So here, this is at eye level, you are going to read the correct volume, that is 1930. If you read from above, you are going to read a lower volume. If you read from below, you are going to have to read a higher volume. That's why it's important to be in the correct line of sight. And what else is here in the right tab? This is the setup. And let me see, acetate titration. And here, okay, just to complete this introduction, once you we obtain the end point, you are going to calculate the molarity of acetic acid. How do we calculate the molarity? We know we have the volume that we use in the burette of sodium hydroxide. We have the molarity of sodium hydroxide that is given, is our titrant, and we know the volume of vinegar that we titrated. And we know that the reaction is 1:1. Let me see if it's written here. Here, this is acetic acid. 1 mole of acetic acid reacts with 1 mole of sodium hydroxide. So the reaction is 1:1. That means if I know the number of moles of sodium hydroxide that I used in the titration, I will know the number of moles of vinegar that I have, because it's 1:1. And how easy it is to calculate the number of moles of sodium hydroxide. It's very simple. It's just multiplying the concentration times the volume. Here is telling us the moles of sodium hydroxide. Here, how it is the volume that I used in the titration. Usually it's final volume minus initial volume, multiplied by, here it says, number of moles of sodium hydroxide per liter, which is the concentration, the molarity of sodium hydroxide. And then we know, as I show you in the equation, that the number of moles of acetic acid in the vinegar equals the number of moles of sodium hydroxide. So then all we have to do is, in order to calculate the molarity of acetic acid, is just to divide by the volume of acetic acid. We will do it together when we get to the report part. And the last part of the report for you is to calculate the mass volume percent. We will do it together. What is the mass volume percent? Is the mass in grams of acetic acid in 100 milliliters of solution. So how do we calculate the grams? we have the number of moles of acetic acid. So we multiply by the molar mass and we calculate the grams of acetic acid. And all we have to do is divide by the volume of acetic acid. So this is basically the first part of, just the introduction and to go over the write-up of the experiment. Any questions so far? Okay, so then we will continue with some practice problems, and then we will go over the report. Let's see if we can do this together. Let's read the first practice. Determine if the following substances are acids or bases. You can actually send me a message. 1A. What do you think is 1A? It's called perchloric acid. How do we recognize that A is an acid? Because it has an H as the cation. So then you are going to say that this is an acid. How about B? Ammonium, NH4+. Is this an acid or a base? It is also an acid because it can donate a proton. So it's also an acid, NH4+. It can donate an H+ plus ammonia. And because it provides a proton or an H+, it is an acid. A is a strong acid, it's perchloric acid. Perchloric acid also has an H as a cation, and we recognize 1A as an acid. How about C? Instead of, yes, Rusia, thank you, perfect. C is a base. Very good. It has the OH and it dissociates. Very good. OH. When you see OH, yes, it is a base. And also it can accept a proton. This is another definition because the OH combines with a proton to form water. D is a little bit harder because we don't see the H and we don't see the OH. So this is harder. But if you encounter one of these, what are you going to think about? You are going to think that this is an anion and it comes from, this is hydrochloric acid that dissociates. Yes, it is exactly. Very good. It is a base. Exactly. Because it is the conjugate base of hydrofluoric acid. So you can add the H, because hydrochloric acid, and if this is the acid, this is the conjugate base. So it is a base. Exactly. Very good. How about E? That's a tricky. First of all, we look, can this hydrogen bicarbonate donate a proton? Okay, this one is a tricky. So what do we ask? We have HCO3 minus, right? Very good. So the first thing that we ask, can this ion donate an H? If it can, it's an acid. Yes, because it has here this H. So we can say, but we have to ask both questions. If the bicarbonate can donate an H plus, it's an acid. But then we have to ask, can this ion accept a proton? If it accepts a proton, it's a base. And if it can do both, it's both. It's amphoteric, like the water. So let's look in this case, because of it can donate, this equation said it's an acid. Now we are going to see if this HCO3 minus can combine with an H. Can it? Yes, because it can form carbonic acid because it has two. For this equation, that it can accept an H plus, it can react and combine, then it's a base. So what do we discover? That it can be an acid or a base, both. It can release an H or it can accept an H. So it is both. Very good. And then the question number 2, any questions here? Okay. Okay. So now let's go to question number 2. It says, what is a neutralization reaction? We saw a little bit. We saw that we said that it's a reaction between an acid and a base. This is an acid. This is an example. To form the H is going to combine with the OH to form water. Yes, awesome, exactly, very good. And the Cl is going to combine with the sodium to form the salt, sodium chloride. So if you see, this is a type of double replacement where ions switch partners. The H was bound to the Cl and decided to go to the other anion, that is OH. So it's a reaction between an acid and a base to form water and salt, exactly as you said. And that's basically it. Not more about neutralization. And let's see what else. Do we have another question here? Okay. What is it saying here? What is the setup of the titration? We saw that. We have here, you have a flask, and then you have the burette. Sorry, I'm so bad to draw. And basically, you have the analyte here, and you are going to pour with a. This is kind of the setup. You have a clamp to hold the burette, otherwise it's not gonna stay in the air. Oh, thank you, thank you. Okay, so this is the setup. And now a question. What solution goes inside the burette? Here we have the burette is going to be filled with the base that is sodium hydroxide in our case. And what is important is that the burette can measure the volume precisely. So for us, it is important. We are going to use the volume of sodium hydroxide that we added, base B, C acid. What is the name of the solution inside the burette? Okay, you said C is acid, B is a base. Okay. Look at the question. What solution goes inside the burette? And we said the base. This is the burette. Yes, you were actually answering the next one, I think. Yes, exactly. B is base. Yes. And then the C, what is the name of the solution inside the burette? Remember, because they might ask you the proper name. And it's called the titrant. The titrant. Let me write it here because my pronunciation here. Okay, the titrant is basically sodium hydroxide. Is the solution that goes here. So, and the titrant, I'm now in the C, because it says what is the name of the solution inside the burette, and it's the titrant. Is the solution that we add slowly to record the end point. The end point will be when the flask, it will turn light pink. And so this would be the answer to C. And then D, it says, which one is the analyte in our experiment? Analyte, remember, is the unknown. So the acid is our analyte, is the one that is going to be in the flask. So the titrant is what we know. The titrant is the base, but it's the substance that we know the exact concentration. We know the molarity of the sodium hydroxide that we are using inside the burette. And we are going to know the volume, and that is known. But in D, it says the analyte is what it is in the flask. In the flask, we have the vinegar that contains our acid. So the acid is our analyte. Yes. Is this clear or so? What part would you like me to repeat? Should I repeat the question C? Okay, awesome. Okay, so C, we know the burette, and then D is our analyte. We said that the acid is our analyte, and it is the substance in the flask that we are trying to calculate the concentration. We don't know how many acetic acid we have in the vinegar, and that is our analyte. And then the F, what indicator we add? In this experiment, we add phenolphthalein, that when we start is colorless, and at the end point is light pink. And the question is here, what is the color of the indicator at the end point? And we know that the phenolphthalein, we said, has no color in acidic solution and has a pink color in basic solution. So why it turns pink? Because we have the acid in the flask, and once all the acid reacted with the base that we are adding slowly from the burette, we reach the end point, and then with the end point, it's neutral. Neutral means the same concentration of hydronium as hydroxide. But if we add one more drop of the base, then the phenolphthalein will turn pink. So the excess of the hydroxide ions will make this solution pink, but just one drop. And then is when we record the volume. And let's look at the question 4. What aspects of the titration are important? Try to remember that as well, to obtain a good result. Number 1, if you want to be precise in a titration, number 1, well, we have to make sure that we do not pass the end point to record the correct value of the volume of sodium hydroxide. So the first is the end point. Let's say that we see a light pink and we continue adding base. Well, we are going to record a different volume and it's going to be wrong. So as soon as you see the light pink, stop. Do not pass the end point. Number 2, important, to read the volume at the correct line of sight. And that's what we saw before. The meniscus should be at eye level. If we have the liquid, we read the lowest part of the meniscus, and our eyes has to be at the right level. What else is important in a titration? That when we fill the burette with our titrant or our base, we check that there are no bubbles in the burette before we start. Because if there are bubbles, we are going to record a volume that is the volume of the air or the bubbles plus the volume of the base. So we want to make sure there are no bubbles. And also, just to remember but that's something that you are not doing it, but the volume markings in the burette we have a 0 here, and the volume increases going down. And then we always have to report the readings with one estimated digit past the smallest marking. That's what you saw in the experiment number 1. Always, if you have 0 ml and you have 1 ml, you are always going to estimate one more digit. So if you do all that, this is all important aspects to make sure that you obtain a good result. Any questions before we go to the report and try to see how to complete it? Okay, so let me share the report here. This is an empty report. Everybody has different data. So the first part of the report, you're gonna see something different. Everything that is in red, because you are not doing the experiment in the lab, is the data that is given. So the first part, it will give you an indication. This is just all the data. So you will see, oh, the vinegar, they are using 2 different ways to measure the pH. They are using a pH paper, which is a paper that has different colors depending on the pH. And then they check the color of the paper with a scale, and it says pH of the solution. And they are also using a pH meter that is much more effective. It's closer to the pH. So first of all, this is all data that you are going to see. You don't have to do anything. This is the data given. And this is the first thing that you have to do. Basically, they are saying, okay, determine the pH. All you have to do is right here, if the pH given is acidic, basic, or neutral. So let's look at vinegar. Just to refresh, when the pH is neutral, when the pH is 7. When is the pH acidic? When it's lower than 7. When is the pH basic? When it's higher than 7. So for the first one, let's look at the pH from the pH meter. 2.3. Is this pH acidic, basic, or neutral? Yes, exactly. Very good. How about ammonia? The pH is 11.5. Is higher than 7. Is it acidic, basic, or neutral? Let me see. You wrote neutral. Is that right? Okay. So we are looking at 11 point. Okay. If the pH equals 7, then the pH is neutral. Oops. What does it mean, neutral? Neutral means that the concentration of OH minus equals the concentration of hydronium or protons. Now, if the pH is higher than 7, it's a basic solution. If the pH is lower than 7, it's going to be, oh, very good. Okay, very good. So ammonia is higher than 7, is a basic solution. How about lemon juice? You look at here, the pH is 2.4. Is lower than 7. Yes, very good. So that is, you continue completing this. This should be easy, and it will give you an idea of the shampoo that we use every day or the detergent, if we are using acidic or neutral, and you can complete based on just this, to complete this part of the experiment. Then the next part is what you have to complete is basically they are telling you here, you can read the procedure in the write-up in the PDF. If you have any questions or you have to refresh, you can always go back because it will tell you step by step how they did the experiment, like if you happen to do it or if you had to do it in the lab. In this case, let's look at the first one. You have H2O, you have water. You measure the pH, and they are telling you that the initial pH of the water is 5.1. And then you add 5 drops of acid. When you add acid, the pH becomes lower because it's more acidic. And it says that after 5 drops, the pH dropped to 2.7. Then after 10 drops of acid, the pH became 2.3. The first thing that they are asking for you to complete here is the pH change, which means after the 10 drops of hydrochloric acid, what was the pH? And it says that if the final pH is lower than the original pH, the change will be a negative number. And that is our case. The pH change will be final pH 2.3 minus 5.1. And that is a negative number. That is minus 2.8. So this is the change in the pH. And then they will ask you, is this a buffer or is not a buffer? What do you think? Is the water a buffer? We saw what is a buffer. And we also see how much the pH change. If we have a buffer, the pH won't change that much. So is this a buffer? Yes or no? The pH change is actually no buffer. Why is no buffer? Because the buffer, we said that is a weak acid with a conjugate base, is a substance that makes the solution resist the change in pH. And here we see that the change in this pH is minus 2.8 points. it changes quite a bit. So it's not a buffer. It's just water. Water is not a buffer. It didn't resist the pH when I added acid. The pH became more acidic and it changed in minus 2.8 points. So we are not in the presence, in this case, with a buffer. Let's look at the second. The second, again, you are going to do the original pH is 6. Okay, sorry. Okay, I see. So basically, okay, so but when you see a buffer and you add an acid and you add a base, the final pH or the difference in pH before the final and the initial does not change much. For example, the initial pH here of the solution of salt, sodium chloride, is 6.7. Then after you add 10 drops of acid, the pH is 3.8. So the pH change, how much it changed, it will be final minus initial. 3.8 minus 6.7. You will have different data. Each one has different data. For me, thank you, exactly, minus 2.9. That's a big difference in pH, almost 3 points. Is this a buffer? Almost 3 points. Is again no buffer. Yes, a buffer, yes or no? No, because we don't have a buffer. When I add an acid, exactly. Now let's look at when we have a high pH buffer. We have a buffer that works better with higher pH, which is basic pH, when the solution is basic, but it's still a buffer. So the initial concentration is 9.8 of the buffer. I added an acid and it changed to 9.2. So the change in pH is 9.2 exactly minus exactly 9.8. You said minus 0.6. That's less than 1 point. Is this a buffer? I added an acid and the pH was nearly constant. Are we in the presence of a buffer? Yes, it is, exactly. And the same with the next one that they are telling you it is a buffer. So the pH change here, 3.8 minus 4.2, we have a minus 0.4, even less the change as before, because this is a low pH buffer. Works better than the previous one, because works better when we have low pH. So the works better means that the pH change is nearly constant. Yes, it is. Awesome. Perfect. Okay, so this is the first part of the experiment, and then you have to do the same. The first part is when you are adding 10 drops of an acid, HCl. The second part is similar, but you are adding 10 drops of sodium hydroxide. You are adding a base. So let's see with my data, what is the pH change that I should write here? You can text me or message me. Yes, exactly. Now it's positive because exactly. That's a lot of change. 6 points. Are we in the presence of a buffer? No, very good. Same here, you completed. And how about the low? Let's do the high pH buffer. What is the pH change? Yes, very good. Are we in the presence of a buffer? Yes. It's nearly constant, 0.2. Exactly. And similar here, we have another buffer, and the change is also small, but a little higher than the previous one. I got 0.7, I think 5.1 minus 4.4. Okay, it doesn't matter. It's still small, less than 1. But yeah, I'm with glasses. Without glasses, I don't see anything. Yeah. Okay, so this is the first part. Let's continue here. Then comes the part of the acid-base titration. They are giving us the information. How much vinegar we had in the flask. We have 5 ml. It says that it should have about 5% of acetic acid. They're telling us that we should get something similar to 5 because in the label it says that 5% of that vinegar is acetic acid. They are giving us the molarity of the sodium hydroxide or the titrant and the volumes. The initial volume means when we had the burette, before we started, how much volume of, and here we have the flask, right? With our vinegar. So initial volume, let's go to trial 1. The initial volume, let's say, was 0.42. Then you open the stock cock, and you did the titration, and the final volume is, after you finish, is it went down, the titrant, you use titrant, and you read 43.01. So they are asking, what is the volume of sodium hydroxide used? What are you going to write here? And here, and here. How do I know if I have the final volume of the burette and the initial volume? How do I calculate the volume used? It's going to be the final volume minus the initial. So for this, in this case, trial 1, I do 43.01 minus 0.42. Exactly. Very good. So 42.51. Very good. The same way you do trial 2 and trial 3. And then they ask you, what is the average volume? How do you do the average volume? You just do, this is V1. The average volume is going to be volume 1, this is volume 2, and this is volume 3. Plus volume 2 plus volume 3 divided by 3. So this is how you complete this part. In my case, you will have different data. I have 42.75 milliliters. This is with my data. Then they ask you the average volume in liters. All you have to do is divide by 1,000. So for me, it's 0.04275 liters. Then moles of sodium hydroxide use. And it says that use the average volume. So how do you calculate the moles? That is simple. I am here now. The number of moles of sodium hydroxide is going to be volume. We have to, in this case, we still don't use the molar mass. In order to calculate the number of moles of sodium hydroxide, we just multiply the volume that we use in the burette, and we are going to use the average volume, the volume in liters times the molarity of the sodium hydroxide. We have the molarity because it's given, is here, 0.0971, because the number of moles is always volume in liters multiplied by molarity of the solution. So this is the formula that we are going to use, because actually molarity is number of moles per liter. And this is we multiply by the volume, and we end up having the number of moles of sodium hydroxide. Let's see, number of moles of sodium hydroxide. I know. So this one maybe is going to be easy, because look, number of mole of sodium hydroxide. If you know what is the molarity, they are telling you, let's try not to memorize. Number of moles is going to be, let's see, they are telling you molarity of sodium hydroxide. What does that mean? 0. Let me see if I can type, because this is okay. So 0, yeah, much better. 0.0971. When they say big M, that is molarity, is basically moles per liter. And you multiply that by the volume that you use, the average volume in liters. So that will be 0.04275 liters. So because the molarity is moles per liters, if you multiply by the liters that you use, which is the average of the 3 trials, then you just obtain basically the number of moles of sodium hydroxide. With my data, 0.04185. Does it make sense? Basically multiplying, that's something it will be useful to remember. If you multiply the molarity, which is moles per liters, by the volume that you use in the titration, you obtain the number of moles of sodium hydroxide, because they are telling you, okay, the molarity is how many moles in 1 liter, but you don't care about how many moles in 1 liter. You care how many moles of sodium hydroxide are exactly in the volume that you used in the titration. And once we have that, we have the volumes. They are asking you in here, what are the moles of acetic acid? How many moles of acetic acid? And you perfectly know that in the titration, you have a base, sodium hydroxide, that reacts with the vinegar. I'm going to abbreviate HC as acetic acid because it has only one H, and sodium hydroxide has only one OH. So this neutralization reaction is also 1-to-1 ratio. 1 mole of sodium hydroxide reacts with 1 mole of acetic acid to form sodium acetate, which is the salt, plus water. But we are interested, we know how many moles of sodium hydroxide we used in the titration. And that is this number that I wrote here, 0.04. And how do we relate to the number of moles of acetic acid? Is 1 by 1. The molar ratio is 1 by 1, which means the number of moles of acetic acid is going to be the same as the number of moles of sodium hydroxide. So this number goes also in here. It's pretty messy. Any questions there so far? Okay, so now we calculate the number of moles of sodium hydroxide. Then we calculated, we know it's the same number of moles of acetic acid. And now all we have to do, they are asking for the molarity of the acetic acid. And we know the definition of molarity. Molarity equals number of moles, in this case of acetic acid, I will abbreviate as AC, per volume in liters. So we have the number of moles that we used is the same as the base, 0.004,185, divided by the volume of acetic acid that I added in the flask. So if I look here, how much acetic acid I use, volume, how much vinegar, what is the volume here? I come here, volume of vinegar used in milliliters. I used in the flask here, I added 5 ml of vinegar. So when I will calculate the concentration of the molarity of the acetic acid, I need to know the volume of acetic acid. I have to write the volume in liters. So I will write 0.005. And that is in liters, and that will give me a number that is, for my data, 0.005. Yes, thank you. 837 molar. Very good. And then they ask what is, so we did this part, and then they ask for the mass of the acetic acid. That is easy because you have the moles. Every time you have the moles and you want to convert moles of something into grams of something, the same thing, you use the molar mass. So in our case, we have, how do we calculate the mass? We know the moles, so the mass of the acetic acid is going to be the number of moles that we know is 0.00418 times, and that is moles multiplied by the molar mass of the acetic acid, that is 60.1, is given in the write-up, grams per mole. Moles cancel, and for me, I obtain a mass of 0.2. You will have a different data in your report, but grams. And the last question is the percentage, mass volume. And that they are giving you the formula, and that is very simple. Is basically the percentage mass volume is the mass of the acetic acid that you just calculate, 0.252 grams, multiplied by 100, divided by what? Divided by the volume of the vinegar in milliliters. Because what this means is how many grams of acetic acid are in 100 ml of vinegar. When I do this calculation, I obtain 5.03%. And it should be around 5 because the label here, it says 5%. So you should get a number similar to that. Exactly. Very good. And now we are going to conclude the workshop here. I will stop the recording and I will stay in case you have any questions that you would like me to answer. And thank you for coming.